Clarence, you're muted.
Okay, I'm going to end the polling now. Oh, there's 14 people now that are showing up on our polling thing. I think I'm going to have to end the voting right now, ain't I, David? And polling?
Yeah, if you want to, if you don't want to
Yeah,
wait.
we're going to have to.
Okay, then you just hit share results so everyone can see it.
Okay, so now 92% of you got that right. One person did not. If we increase the pressure from 30 psi to 60 psi with the same resistance, we are going to double the flow, and that's going to happen. And then that looks like a 50-50 then. A good working circuit. What pressures can we expect at pressure gauges 1, 2, and 3? So at 1, 2, and 3, we should be expecting 100 psi, 100 psi, and 100 psi. And then the other one, we should, people picked 100 psi, 100 psi, and 3 psi. A lot of you guys picked this one that has a at 3 psi on the third gauge. What am I missing here? Why didn't you guys get that? The right answer in the good working circuit is like as it's shown right there is 100, 100, and 100. And then some of you guys picked 100, 100, and 0. Well, if you had 100, 100, and 0 right here, that means you have a restriction there, and that's not a good working circuit. And it looks like more of you guys did that than more you guys got that wrong than got it right. Anyone that picked the first one was the right one. What is it with this question that, because I think you guys know better that, what's wrong with this question that you had a difficult time coming up with the right answer? Or maybe you didn't have the circuit up right away and you were kind of, it took us a while to get the circuit up and you might have answered that question. That's about the only way I could kind of think that you guys were doing some lights on. Here we had a 50-50. Let's go down here. Here we got more of a 80% got it right. Going a little further, we got about 75% getting it right. And here we got 20 valve does not switch if turned on. Well, let's go these one at a time. The airflow increases by 2 times because we have increased the tire pressure by twice. So that basically you got. In a good working circuit, what pressures can we expect at pressure gauges 1, 2, and 3? 1, 2, and 3. Some of you said you wanted 0 at that one. This is the guy right here. Anyone that picked 0, can you tell me why you might have picked 0 since we all knew these were going to be 100, 100, 100? I don't know if my
question is that wasn't up yet. We thought 3 was down below the motor.
Okay. And so you might have answered. So did you answer that question before you saw the circuit? Because I was.
Yeah, we're just looking to eat real quick, and we were going off memory, and we thought 3 was below the auger.
Okay. Okay, that's kind of what I thought was the issue there. Let's go on to, well, we'll have to get the circuit out next time before we do this. And so then the third one that comes up. The load requires high pressure on one side and 0 on the other. In a good working circuit, what pressures can we expect at 3, 4, and 6? 3, 4, and 6. Again, you guys, at 3, 4, and 6, we're looking for 120, or 100, 0, and 0. So 100, 0, and 0. Most of you guys got that. Maybe we got the circuit up by that time that you could be answering this correctly. The solenoid valve is, now we're going with the, okay, the solenoid valve switch is turned on. The auger motor runs at half speed. So all gauges are correct except 4 and 5, which reads 50, 4 and 5 would read 50 PSI. That means there's a restriction between 5 and 6. Most of you guys got that. If you have 50 PSI there and 0 there, there's a restriction there. Very good. Okay, now we got solenoid valve switch is turned on. The auger motor does not turn. Gauge 1's 100, and the rest is 0. 100, everything else is 0. So the choices are: the motor's bad, there's a restriction between 2 and 3, but the restriction between 1 and 2. 92% of you got that. And then somebody said burn, open coil, and then normally close decision on the solenoid. Yeah, that could have done it. So you guys did right. So A and B was correct. I mean, C and D was. Nice job. I'm not feeling so bad. The solenoid valve switch is turned on. The auger motor does not turn. Gauges 1 and 2 read 100. Gauges 1 and 2 read 100. And my motor does not turn. The motor is bad. Restriction between 2 and 3. And yes, you guys, 100%. Very good. I'm impressed. Solenoid valve switch. The auger motor does not turn. Gauges 1, 2, and 3 read 100 PSI, and the rest read 0. The motor is bad. Very good. Okay, now I'm feeling a lot better now. The solenoid switch is turned on. The auger motor does not turn. Gauges 1, 2, and 3 read your 100 PSI. 100 PSI there, that's good. And all the rest reads 0. That means the motor is bad or the motor's overloaded. Fabulous. 100% on that one and 92% on that one. That is really good. Both of those apply. Motor's bad, motor's overloaded. And the solenoid valve switch is turned on. Auger motor does not turn. 1, 2, 3, 4, 5, 6 read 100. 1, 2, 3, 4, 5, 100. This here reads 0. There's a restriction between 5 and 6. That's true. That should be 100%. And there's also the filter is plugged up. As the restriction between 5 and 6 is the same as the filter. Thank you very much. Number 10, solenoid valve is turned on. The auger motor turns to half speed. Gauge 1, 2, and 3 read 100 PSI. Okay, what are we talking about here? And the rest read 0. So the motor's bad. You got that up. You got that right again. All these things are there, and all the zeros are there. The motor's bad was it is the proper one. You guys did a fabulous job. It was that third one. I took too long of getting this up. Something that thanks for pointing out that, Dave. And so then I was going to go to, I think we're
in a series circuit, when one part of the circuit fails, the symptoms are usually the same.
I think we were in the safe meter usage too.
Yeah, I think we're like 5 minutes into the second one.
5 minutes and 46 seconds, or 5:27. Why do I have 5:46? Because we did go through that. So very good. So I think this is where we're at. Went through this part, which cut off the unneeded.
SPDT. The armature is considered the pole, and the fact that the armature has a closed and open terminal to contact makes it a double throw.
think we were starting to probably walk right into timers.
Relay coil, high current contacts, and an attached overload relay below it. Relays are just special relays in that their contacts actuate at different times than normal relays. Relays could almost be considered 0-second time delay relays. These timers have times that can be set with switches and knobs. Some timers are a dedicated type, such as delay on break, delay on make, single shot, etc. Some are so fancy you can pick and choose the type by rotating a knob. For more information, download the timer.pdf. Make, BMR. Upon application of power to the input terminals, the time delay begins. At the completion of the pre-selected time delay, the output contacts transfer. Reset is accomplished by removal of input power. There is no false output when reset during timing. Delay on break, BBR. Power must be applied to the input at all times prior to and during timing. Upon closure of the initiate switch, the output contacts transfer and remain transferred if no further action is taken. When the initiate switch is opened, the time delay begins. At the end of the pre-selected delay period, the output contacts revert to their original position. Removal of input.
What I'm trying to get to, you guys to think about is that you're going to see some relays in your circuit, then you're going to see some timers in your circuit, and there's little timing setups that you do that you go, okay, this is what I need to have done. Sometimes when certain things happen, you're going to want a certain amount of time to happen afterwards, and then something else happens. That's and you normally use a delay on make to do that. And then maybe you're going to want to delay on break. That means if something happens, it's going to initiate, it's going to close its contacts right away. And after a certain amount of time goes by, it's going to take it away. That's a delay on break. Then you can have a single shot that anything time something happens for a certain amount of time, it's just going to energize and then de-energize. These you've got to understand your timing circuit, exactly what it does do. So when you're doing some troubleshooting, you're waiting for that time to happen when you're looking for something to happen.
Put power will reset the control. Single shot. Stop touching 1, 2, 3, and now
Okay, now let's get
but has
back to the
not yet
relay.
actuated the switches.
So looking at the bottom of these little buggers, you're going, wow, what do we got here? Well, you've got like octal base. This fits into an octal base. The one I got there, octal stands for 8. Then this gets to be like an 11 pin. This here has got 1, 2, 3, 4, 5, 6, 7, 8. So this is an octal base here. This here also has 11 pin here. If you remember doing a single pole double throw, we had 5 terminals. We had 2 of them from our coil. Then we had C for the C contact, and then the NO and NC. That was 5 terminals. That was a single pole double throw. So if you go to a double pole double throw, we're going to have 3 more terminals for that set of contacts we're adding. So you're adding 3 to that 5, and that gives us 8. And then you're going, okay, maybe I want a triple pole of my double pole. So you add 3 more contacts, and that gets you 11. So you've got like your 11 pin relays, your 8, and so on and so forth. This here looks at the bottom part of it. This is your a relay. If you look at these 2 right here, this goes to your coil on your electromagnet. That's A and B. All you gotta do is put 120 volts on one side and 0 on the other. Or if it's DC, you put common or 12 volts or 24 volts, whatever that relay coil is. You can get relay coils for DC and AC. You can get some coils that do that will energize on 480 volts versus 240 or 120 or so it's kind of like mix and match depending on what your power supply is. These are your triple pole double throws. This is the same thing as what we have here. They just didn't decide to show it there because it was too hard to see by adding those, but this here is going to mimic that. So if you go from your, this is your, like your C contact on the one big relay that we're looking at, that went from C to NO and NC. You take from 7 to 1. This is your, 1 is your NC contact. 4 is your NO contact. This is your armature right here. When you energize this, this is going to toggle from 1 to 4. So, and this is going to toggle from 3 to 6. And this is going to toggle from 2 to 5. Same thing you have here. This kind of gives it a different look. This here is your single pole, double. This is your triple pole, double throw. 1 pole, 2 pole, 3 pole. Here's your 9. Here's your 8. Here's your 7 right here. This is your common side. Whenever you energize this, 7 is going to go to 4. You energize it, 7 is going to go to 4. 8 is going to go to 5. This 8 is going to go to 5. This 9 right here is going to go to 6 when you energize it. So this is your relay. Normally open contacts, normally closed contacts.
A 3P-DT triple pole double throw relay. Whenever the coil is energized at terminals A and B, poles 7, 8, 9 stop touching 1, 2, 3 and now touch 4, 5, 6. The plus and minus polarity on the coil terminals refer to relays with DC voltage coils. Analog input and output boards are where the rubber meets the road when it comes to computers and wiring to the plant. When the computer tells the plant to do something, an LED lights up the output for that task to be performed. The signal is sent to a solid-state, black, relay, and power is sent to a starter or solenoid, etc. The computer listens to the plant when gates are all the way closed, or an asphalt meter or belt scale is reporting its status and rate through yellow, white, red, etc. colored input modules. The black modules are 120 volts AC relays with contacts that energize when the corresponding LED, 13, illuminates. When the contact closes, the black wire above it has 120 volts AC power to the terminal with the black wire on it, the terminal just above the black module. The black modules are probably used to energize solenoid valves to open gates and valves. If the LED lights up, the computer is asking that module to energize the solenoid valve. If the solenoid valve does not operate, check for 120 volts AC at the terminal. If there is no 120 volts AC, the replaceable fuse or module is bad, and one should be replaced. The pencil is pointing to a fuse, which looks like a resistor. It can be pulled right out. The yellow modules are 120 volts AC input modules, connected to limit switches on the plant to report the position of gates, etc. The yellow input modules have corresponding LEDs that illuminate when the limit switch input supplies 120 volts AC to their terminals. If the limit switch places 120 volts AC at a terminal, expect the LED to illuminate. If the LED does not illuminate, change out the fuse or yellow module. Sometimes the modules are different colors, sending or receiving different types of signals than described above.
Computer reports a gate did not open. Several things may be the problem. Choose all that apply.
Chris, I'm going to pick on you. Is A true?
Yeah, Clarence.
Yes.
Chris had to step out for a minute.
Okay, who's talking?
This is Jeff.
Hey, Jeff, is A true?
Yes.
Okay, computer reports the gate did not open. The fuse supplies that black module is burned. That could be true. Okay. How about the yellow module reporting the gate status is bad?
I would say that could be true.
Yeah, because your computer wouldn't know if that opened or closed, and so therefore it reports that. So I would say that's true too. Not bad, Jeff. Okay. How about C? The fuse to the yellow input module is burned
True.
because it didn't report going back. And go, okay, the fuse would have kept that from doing it. You know, the module telling to open up, and then if it did open up, then come back, and then did that report it? So we're looking at a report. All those are true so far. Great. Um, how about the solenoid? Is a solenoid good or bad? Do we know? Could it be bad?
Well, it could be.
And it could be good too as well, couldn't it?
You skipped over D there, Clarence.
What's that?
You skipped over D.
Black module supplying to the gate solenoid is bad. Would that cause it?
Yeah.
And it's the fact that it didn't report bad doesn't mean either way if the solenoid is good or bad. Is that correct?
Correct.
So so the solenoid could be good and the solenoid could be bad. So if my way of thinking, I think all of those. Let's see what's happening there.
Apply.
Okay, let's bypass. I think the computer reports the gate did not open. Several things may be the problem, but the solenoid being good wouldn't be part of that problem. So I take back the fact that I would have picked E. So I think you did a really nice job there. Thanks a lot, Jeff, for standing in for Chris. Someone's got to cover him.
The correct answers are A, the fuse supplied to the black output module is burned. B, the yellow module reporting the gate status is bad. C, the fuse to the yellow input module is burned. D, the black module supplying power to the gate solenoid is bad. And F, the solenoid is bad.
Stop switch on the left and an E-stop switch on the right. The start switch is normally open, NO, and the stop switch is normally closed, NC. The operators on the stop and start are spring-loaded and they are actuated momentarily, and as long as they are being depressed, the E-stop switch is spring-loaded normally closed, NC. Some E-stop switches are push-pull. A selector switch is on the center right. It could have 2 or 3 positions. Its operator could be maintained or spring-loaded. The selector switch can have several contact blocks, both NO and NC, that are stacked up behind it. When you turn the selector, there is a piston that goes down one side and will open and close the contact blocks on that side. On the other side is another piston that will open and close the contact blocks on that side. The limit switch on the bottom could monitor your asphalt valve. It is spring-loaded to one position. In that position, the normally open NO contact will be open, and the normally closed NC contact will be closed. When the limit switch is actuated by a mechanical device, the contacts will switch states.
This stop switch has normally closed contacts and the ohm meter reads 0 ohms. If the selector was set to continuity, the beeper would be chirping.
The contacts are actuated, and therefore the ohm meter reads infinite resistance. To the start button, the meter reads infinite resistance across the normally open contacts that are not being actuated at this time. Meters require no power on the circuit, and it is important to isolate the circuit being checked from the rest of the circuit. Sometimes a wire needs to be disconnected in order to isolate. In order to completely check out a switch, it should be effective in both states, both open and close. Tell us about temperatures and pressures. The device at the top left is an electromechanical temperature sensor made by Allen Bradley. It uses mercury-filled capillary tubing to sense temperature via vapor pressure technology. The normally open NO contact will close at the selected temperature, and the normally closed NC contact will open at the selected temperature. If this temperature switch was set to 300 degrees, the NO would close at temperature rise of 300 and above, and the NC would open at temperature rise of 300 and above. The device at the top right is a pressure switch. It can be used to ensure that the oil pump is on so that there is hot oil flowing or to control the operation of an air compressor. The normally open NO contact will close at the selected pressure, and the normally closed NC contact will open at the selected pressure. If this pressure switch was set to 100 psi, the NO would close at pressure rise of 100 and above, and the NC would open at pressure rise of 100 and above. The device at the bottom left is also a pressure switch. It can be used to monitor the operation of the blower at the burner. The normally open NO contact will close at the selected pressure, and the normally closed NC contact will open at the selected pressure. The photohelic device at the bottom right is a very sensitive air pressure switch. It can be used to monitor suction at the front of the dryer. This can be used to open and close the damper automatically. The normally open NO contact will close at the selected pressure, and the normally closed NC contact will open at the selected pressure. This is a very good device to have in a plant to automatically control the damper. It provides very important control, inexpensively. Voltage. The voltmeter selector switch is set for AC volts, and the voltmeter test leads are connected across 2 points of potential difference. This is an auto-ranging meter, and the value should read 120, and the engineering units displayed should be volts AC for volts AC. It is important to focus on reading the engineering units since the meter is auto-ranging and may be reading a mere 120 MV. When measuring the 12 volts DC battery, the voltmeter selector switch is set for DC volts, and the voltmeter should read plus 12 volts DC, since the red lead is on the plus terminal and the black lead on the minus terminal. If the leads were changed around, the meter would read minus 12 volts DC.
To use this voltmeter, connect the red test lead to the volt-ohm input and the black lead to COM. Set the function range switch to the desired AC or DC voltage range. Touch the probe tips across the voltage source in parallel with the circuit and read the value. Consider the polarity for DC measurements. To measure voltage, the voltmeter test leads are connected across 2 points of potential difference. This measurement is taken in parallel with the component being tested. With the meter leads in their proper location on the meter and the manual range properly set to a higher range than that expected to be measured, connect the meter in parallel with the component being tested. Apply power to the circuit and reduce the range of the meter so that a reading cannot be obtained, and then move it up 1 range. Caution: the mistake of connecting a voltmeter in series does not damage the meter, but the reading will be wrong. The mistake of setting the meter to AC in a DC circuit or setting the meter to DC in an AC circuit causes the voltage to read incorrectly. This can not only affect your troubleshooting procedure, but can be a safety problem when someone is checking a circuit for no voltage before the circuit is physically touched. Check a known voltage to verify the meter is working.
And how much? 208 volt.
I want to go back over that again.
This lead to the volt-ohm input and the black lead to COM. Set the function range switch to the desired AC or DC voltage range. Touch the probe tips across the voltage source in parallel with the circuit and read the value. Consider the polarity for DC measurements. To measure voltage, the voltmeter test leads are connected across 2 points of potential difference. This measurement is taken in parallel with the component being tested. With the meter leads in their proper location on the meter and the manual range properly set to a higher range than that expected to be measured, connect the meter in parallel with the component being tested. Apply power to the circuit and reduce the range of the meter so that a reading cannot be obtained, and then move it up one range. Caution: the mistake of connecting a voltmeter in series does not damage the meter, but the reading will be wrong. The mistake of setting the meter to AC in a DC circuit or setting the meter to DC in an AC circuit causes the voltage to read incorrectly. This can not only affect your troubleshooting procedure, but can be a safety problem when someone is checking a circuit for no voltage before the circuit is physically touched. Check a known voltage to verify the meter is working.
And how much? 208 volts. Is this AC or DC? AC is the voltage supplied commercially on the electrical grid around the world to industrial, commercial, and residential users. Is this three-phase or single-phase? Normally, when you read 208 volts AC, you are reading a phase of the three phases available. In this case, three phases are available. What would you expect from blue to red? Probably 208 volts as well, since this is a three-phase electrical distribution system.
How much voltage should one read from the blue taped wire to ground?
Where is Chris? Did Chris come back yet?
Hello. Go ahead.
Okay, A is good. By the way, Jeff has been filling in for you, and we decided we don't need you anymore.
That's all right. That just makes things a little easier. I'll give him the keys to the truck.
The correct answer is A, 120 volts AC.
Voltage from blue to ground. The color scheme of the three wires connected to main lugs is the same as the wires attached to the breakers, indicating three-phase. Therefore, the hidden cable is truly a cable without a white tape that would be neutral on a single-phase panel. We don't believe a normal reading from a leg to grounded neutral would be 208 volts. 208 volts is a phase-to-phase voltage on three-phase systems. If we measured from a phase to the grounded cabinet, we should expect 120 volts AC. The transformer is feeding a lighting panel. 480 volt single phase is feeding the transformer primary, and the secondary is providing 240 volts AC. When measuring from the secondary center tap, X2 and X3 leads wire nutted together, or if terminals jumper together, to either secondary leads, X1 or X4, the voltage shall read near 120 volts AC. 140 volts AC single-phase lighting panel can provide 240 volts AC through double pole breakers or 120 volts AC through single pole breakers. This panel has two bus bars tied to each end of the transformer. Every other feeder circuit breaker usually snaps onto one secondary voltage bus bar or the other. When reading voltage from a yellow dot to a red dot, the voltage would be 240 volts AC. This is like reading the voltage at X1 and X4 terminals of the transformer. When reading from red or yellow dot circuit breaker to ground, expect 120 volts AC. This is like measuring from X1 or X4 to the center tap X2, X3. Regarding the outlets, they are polarized, meaning it is important safety-wise to wire the neutral wire and the ground wire and the hot wire to their appropriate terminals on the outlet. The voltmeter schemes on the bottom right show good information to verify your outlets are properly wired. Homemade extension cords can be dangerous if not properly wired. Unqualified people wiring wall-mounted electrical sockets sometimes get it wrong. With your safety glasses on, and you not standing with wet feet on concrete, and your meter set for at least 300 volts, check your outlets for the proper polarity at home and work. When you find a miswired one, turn off the breaker after verifying your meter works, and rewire properly after verifying the power was truly disconnected. You may have to jiggle the probes in the sockets to ensure good contact. Hold the probes near the wire end of them. If the output is
Notice they said hold the probes near the wire end of them. Sometimes when we're doing these electrical things in the classroom setting, these guys would have their fingers down there at the bottom of the probe, very close to the metal tips. I'm going, you don't need to be there. And he says, get your hands, you know, at the end of the probe there where the wire cable's going and be doing some touching that way. Now, do not be part of the circuit. Don't get so intimate with that circuit is what I was telling these guys. And before we powered it up, we put our safety glasses on, and we were typically dealing with 110 volts. At times we were doing stuff with 220 volts. We're going, where do we get 220 volts to be doing some testing inside the class? Is we had a little transformer. And we transformed that from 120 to 220, and that 220 was, we'd send that to the DC motor controls, like you're seeing right here, that's got 220. And our field voltage was always going to be at, or there at the time at 200 volts. And so we had that going to a light bulb. Actually, we don't. We didn't have a 200 volt light bulb. We just checked for voltage to make sure it was there all the time. We actually, in the class, had field voltage at 100 volts. So yes, we did have a light bulb there. And so we, and then we had 0 to 90 volts as far as the armature goes.
is not there, check for proper inputs. If the inputs are okay and the component is not overloaded, then the component is bad. If the bulb is not lit, then check to see if you have 120 volts on one side and 0 volts on the other side. If you do, then check to see if it is burned out or if there is tape over it. There are two components in series at the bottom. One is the input, DC motor control, and the other is the output, DC motor. The output of the DC motor is a rotating shaft. If it is not rotating, check for voltage. It must have an electrical field. If the speed is at 0 RPM, then you will have 0 volts. At full speed, there will be 180 volts. Rule 2. On a good working circuit, the inputs to the load require high pressure on one side and 0 pressure on the other. Rule 3. If the inputs are there and the output is not, the problem is either the component itself or the component is overloaded. Called an AND circuit with an OR circuit at the tail end, unless we were going to wire something to the R4 and C contact. AND means all the switches are in series with each other, and they have to be electrically closed in order to get the light, or the solenoid to energize. Electrically, one of the required inputs to the loads is being met by the neutral being wired directly to one side of the light and solenoid.
Okay, let's talk about that. Here we have a load, and you can see all our loads. This is a ladder diagram. All our loads get to have 100, the neutral is tied to it. And since it takes two things to make this work, we're going to have a hot on the other side. We already got our neutral, but we don't have the second thing that to happen. We need 110 volts here in order for the solenoid to happen. We do have 110 volts here if all these other guys here are made. But in the meantime, we know we don't have anything to our solenoid valve because we don't have anything that limit switch made. So in order to get 110 volts here to seek its low pressure through our load, we've got to have something less than infinite resistance here, like 0 resistance. So we push that down. That looks like a spring loaded, so we need to keep our finger on that all the time. As we're doing that, we're gonna get 110 volts here. This is a normally closed set of contacts on the stop switch, so all we gotta do is not touch it. Don't push it. And then from that point, we got to an R4 set of contacts. Well,
Up
and
to the
so we
point of the
look for
last
a
switch
coil.
passing electrical pressure.
We look for a coil that says R4. Oh my God, here's a coil that says R4. If R4 is going to close, something's got to close switch 1. So if something closes switch 1, R4 is going to close. Then we're going to have 110 volts going through here. TR2 is someplace, and wherever that is, we've got to energize that coil and wait for that time to time out. And then we get to have 110 volts here. If we get to this point right here, we got a manual auto switch. We better have that thing in manual if we're going to get to the next step there. Then we get to this this high-end temperature rise. This could be the temperature switch that you have in your burner control. That's going to shut down your plant if your bags start going over 400 degrees. If it goes over 400 degrees, the temperature thing is going to open up. So in order, so you want it under 400 degrees. So you got to be under 400 degrees to continue to go through. Then we got a pressure switch here. This might be the suction. Might be your photohelix. This is what we got to have. Our suction can't be too high. If our suction is too high, it will open it up. So maybe we have to be under 1/10 of an inch of suction there in order to get past that. Now we go for our gas pressure here. This is in our manifold there. This is our low gas pressure. If our pressure gets too low, it's going to open up. So we have to have adequate pressure. So that's going to close to get that 110 volts there. And then if this limit switch here is going to actuate when you open the gate, then it's going to flow. It's going to give 110 volts there. And then our solenoid valve on that one side is going to have the 110 volts it takes in order to get its job done. Bada bing, bada boom. So kind of gives you an idea how you can logically make these kind of things work on your oil heaters and your burner controls. This is the kind of the logic thing. You say, logically, this is what I want to do. And then you got some controls designer says, okay, that's what you want to do. This is how I'm going to start arranging things in your circuit and make it happen.
Pressures along. A split in the road happens and a choice is being made by the mixing process. If the mixer gate is closed, a light illuminates. When the gate opens, the solenoid energizes. Neither of these happen if the start button is not held depressed, or someone is pushing the stop button, or SW1 is not closed energizing relay R4, or TR2 coil has not been energized and the time duration elapsed, or the auto manual selector switch remains in auto, or the temperature of the process is above the temperature switch set point of 375 degrees, or the draft suction is over 0.25 inches water column, or the gas pressure at the manifold is below 3 psi. These set of conditions can exist at an asphalt plant. Monitoring this particular set of conditions has no real purpose other than for illustration purposes. Switches and controls like this are often used to monitor and control the safety status of burners, material conveying systems, temperature and flow systems, etc. The controls design engineer reduces to simple English terms, and, or, nor, and NAND, etc. The process, the behavior of the process, and how he wants to monitor and control it. From there, he is able to pull together the right components in the right sequence and make things happen his way. To a circuit for reasons unrelated to energizing a load. Resistors are components normally used in complex circuits for purposes such as sending a signal from one circuit to another. The understanding of these complex circuits and their electronic subassemblies is beyond the scope of this curriculum. It is important to understand resistors, particularly those which are adjustable, potentiometers, because by themselves they are subassemblies that communicate to other subassemblies. Consequently, it is important to know if the variable resistance potentiometers are working correctly or not. Potentiometers, or pots, normally have a knob attached to them with a 0 to 100% dial plate mounted to the panel and can be used to adjust the speed of a particular motor. Pots are also used to adjust the volume of radios, the dimming of lights, the voltage signal to speed controls, etc. The pot shown is wired up to be used as a voltage divider. The arrow on the wiper indicates the direction the wiper travels when the shaft is rotated clockwise. If a 10-volt power supply was wired to the two end leads, the wiper voltage of 5 volts could signal a variable speed drive to control a motor to 50% output speed. Rotating the shaft would vary the voltage and consequently the motor speed. Divider speed control circuit, as provided by a typical variable speed drive control terminal board.
Okay. You see that meter is set to read the wiper arm, say W, and that we have a 10-volt power supply. If showed on the previous one that this is a symbol for a battery. It's in your car. So let's say you got a 10-volt battery. These the small side is polarized, goes to your negative terminal, and then the other one is your positive side. And we're trying to signal something to increase and decrease in speed. So as I'm looking at, I'm going to do some annotating here. I'm going to be putting a little box around, I think I can do a box, draw, there we go. Say this was a DC motor controller or a VFD, a variable frequency drive. And you want to be increasing and decrease the speed of a variable frequency drive. It's got some terminals on it that's called speed reference or speed input. And it's going to have like 3 terminals like this. But internal to this VFD is a power supply. It's a 10-volt power supply. So we were talking before, high pressure seeks low pressure. And so this is the return side of our power supply. So we got 10 volts here, and this is our load. So just think of that resistor as a load. This thing in the middle, think of nothing more than maybe your voltmeter test lead, or this is the same signal that's going to go into your variable frequency drive, and it's going to sense as 0 to 10 volts depending on where you put this at. So if we move this wiper up clockwise, that's in this direction here, that means we're going to start getting closer and closer to 10 volts. If this is right in the middle, if we got one lead here on our, and we'll, so I'm going to be putting one test lead here, and you can clip that test lead right to it. I think I'm going to change the color. How do we change the color on that before, David?
I can't remember what the button's called. But there's just like a square, like a colored square. You click on.
Okay, I get it. I see it. So let's say this. This is our black probe, and then the other guy, I guess I should have made him red, left him red, and this is our red probe. We're going to clip our on the low side of the circuit. We always did that right next to the power supply. That's what we were doing before. We're going to do it here. So if we know if we take a red probe and put it to positive, it's going to read 10 volts. If we put our red probe here, it's in our potentiometer right in the middle. If this is a 1K pot, then 500 ohms will be up here and 500 ohms will be down there. That means half of the voltage gets dropped across the top 5 and the other half there. So this is, and since we're measuring from the bottom to where we're at right there, that we're gonna be reading 5 volts. If I start moving my armature up, that middle wiper, the wiper, I mean, that it's gonna start reading 6 volts and 7 volts is what my meter is gonna start reading. And 7 volts and 8 volts and until it gets 10 volts. See on the input to your VFD, it looks at what that voltage is. And it says if it's these 10 volts, it tells that the operator operating that knob is asking for 10 volts. If you start bringing it down to the bottom side, then it's going to start reading 0 volts. And then so up and down, you're going to see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This here communicates to your VFD here. So pretty soon we're going to have some testing going on. What if we, if I give you some symptoms, I'm going to be asking you what kind of things would be causing a problem like that. So as this thing here is going up and down, and you can see it going from 0 to speed to 100% speed, say that no matter where, so say I'm turning this thing up and down, but my speed always stays at 0. Where would be some good checks? We're just talking about the same circuit we had before with the pneumatic, the hydraulic. So if I turn this all the way up to 10, I'm expecting this up to 100. I'm expecting this to go full speed, but it's not. I clipped one of my leads. I put my meter on DC. I set my manual range to 20 because of the maximum, because that's over 10 volts. And then I'm going to take my other red lead. I'm going to do some checking around to see what's going on here. So then I'm going to be asking James, there was Northern Improvement in Bismarck. If I run my pot up and down there and it doesn't change my the speed, it could either be the fact that you didn't ask, you didn't give that VFD a run signal, but now you check, yeah, I did give a run signal. So that's part of what makes a VFD work. If the output's not there, check its inputs. Well, VFD is going to have a couple inputs. One input is going to see the run command. Are you giving a run command? Are you giving a contact close? You flip that toggle switch and say start. So if you did do that, then you got to start looking, well, am I giving it a speed signal? So we're going to be doing a check on a speed signal. So so we set our meter for 10 volts DC or 20 volts DC. So tell me, was it James or Jeff I was picking on? Chris, who was it? It must have been James. Jeff already replaced you. Now James is trying to replace Jeff. Let's see if you can replace Jeff there, James. Where would I go with that? What do I do with my other lead? I got a red lead I got to do something with. Where do I put it?
On your wiper.
I could put it on the plus. I could put it on which is a 10 volt power supply terminal, or I could put it right there on the potentiometer. Or I could put it on the wiper. I could put it on the other side of the potentiometer. Where should I put it?
No wiper?
Okay, so if I put it on the wiper, I can put it on the wiper right there, or I could put it right there on the W. So if I put it on the wiper, what do you expect it?
See if we get 5 volts there.
Okay, and where's your knob going to be set at in order to get 5 volts in?
At 10?
It's going to have to be put in the middle. If you want 5 volts, you got to put in the middle. So if you're looking for 5 volts of the wiper, what are you going to set right there? Is that right?
Yeah, 50%.
at 50%. That's gonna give you 50% speed. 5 volts is half of 10, 50% speed. So I tell you, so you can either put it at the W for the wiper, or you can put it right there at the pot wiper. Say we put it at the pot wiper, and I tell you have 0 volts DC. Then what are you gonna do? Have you determined anything, or do you have to keep on checking?
Keep checking.
Okay, so was that a good reading or bad reading?
What have you got?
That
You
was a
get
bad
5.
Okay, you were expecting 5, you got 0. That's a bad reading. Where are you gonna check next?
Power supply.
Okay, you can check in the power supply right here. Let me say you got 10 volts there. Now where are you gonna check? That's a good reading. That's a bad reading.
Wire. Your
Yeah.
wires are bad.
Okay, you haven't determined yet. You could be checking right here on the pot terminal itself. If I'm on the pot terminal itself and it says, if it says 0 volts, what does that tell you?
That's bad. Not
That's
getting
bad. You
enough
had 10
power.
volts here, you had 10 volts here, you had 0 there, you had a broken wire. That's what's bad. Yes, we were looking at 10. That was the reading we were looking for. But the thing that was bad was the fact that we didn't have the 10 volts. Therefore, we had a broken wire. We had 0 here, 10 volts there. That's the entire pressure drop of the power supply across it. It tells you have a broken wire. What if I had the same problem? No matter where I put the wiper, the speed would not go up and down. And say I had 10 volts here. And I always had 0 volts there, no matter what I did with the wiper. What does that tell you? The inputs
Hey.
are there. What's that?
I'd say the knob is shot or whatever it's called.
The potentiometer would be shot because we had the 10 volts input to it, and that would have been the problem. Thank you very much. Okay, Chris, I'm gonna throw this at you. No matter where I put the pot, I'm going full speed. Where do I start checking?
No matter where you put the pot, you're going full speed.
Yep.
Somebody might put the whopper wire on the 10 volt plus coming out.
Okay, remember that what's happening here in that particular case, if you broke the wire right here, that means you're gonna have 0 here, and you're gonna have that, this is like your filter right here. This 10 volts is gonna build up all the way to where that break is. And so if that's the case and your wiper starts coming down here, it's still gonna be reading that 10 volts, no matter where you put that wiper.
Okay.
So breaking that on the return side is going to cause that thing to go full speed, no matter where you put that wiper. Okay, we'll continue now. I got to take this out of annotate. And I got to do what? Hello. Hello there.
Either click the mouse or just click off of that annotate bit.
Now I'm trying to find out what the annotate thing went to.
Should be at the top of your screen. Share screen.
I don't know anymore.
To 50% output speed. Rotating the shaft would vary the voltage and consequently the motor speed. Divider speed control circuit, as provided by a typical variable speed drive control terminal board. The plus and minus terminals are the 10 volts DC power supply pushing current through a 10K ohms resistor. The resistor requires 10 volts DC, high pressure, on one input, positive, and 0 volts DC, low pressure, on the return side, negative. The voltmeter is reading the voltage between the low side of the circuit and wiper, W. The wiper is adjusted all the way to the top. Consequently, the meter is touching the wiper at the 10 volts DC, high pressure, side of the component and is reading 10 volts DC. Clockwise, the wiper is adjusted all the way to the return side of the circuit, and consequently, the meter reads 0 volts DC. To the middle, half the resistance drops half the pressure drop, and consequently, the voltmeter reads 5 volts, and the speed control knows to go half speed. 3/4 the resistance drops 3/4 the pressure drop, and consequently, the voltmeter reads 7.5 volts, and the speed control knows to go 75% speed. Set to 25%. 1/4 the resistance drops 1/4 the pressure drop, and consequently, the voltmeter reads 2.5 volts, and the speed control knows to go 25% speed.
High pressure seeks low pressure. Current is flowing from the top of the resistor load to the bottom. What voltage do we read between terminal W and terminal minus?
Okay, let me pick on Jim Giuliano.
The correct answer is C, 0 volts DC.
Do you believe that?
This module taught you about components, some
I
circuits,
bet you don't believe that, do you? Okay, let's play it again. High pressure seeks current is flowing from the top of the resistor to the bottom, right like that. What voltage do we read between terminal W and our minus? Which one do you think, Jim?
I'm going to guess, wild guess, it's C.
You weren't listening, were you? You weren't. I didn't ask you guys to pay attention all the time. Thank you very much. Yes, you can see it playing right to it.
I think I
Terminal
might be
minus.
vindicated.
The correct answer is C, 0 volts DC.
This module taught you about components, some circuits, how to use the voltmeter in low voltage applications, and how to use the ohm meter in zero voltage applications. You learned about fixed and variable resistors and the different resistances of various components. You also learned about switches, electromagnetically operated switches, process operated switches, and how they logically do work for us. High voltage applications are discussed in the second part of this module.
Okay, so let me get into this right here. The stuff under your control panel, those are all good things to be able to report information back to. Some of that wire goes to your motor control. And in your motor control, that 110 volts gets mingled in with your 480. It's when you open up those cabinets that you start to get yourself exposed to what's going on. So if you feel safer just with the under the cabinet, that's all good information to be getting, or out there at the plant where there's limit switches and solenoid valves and things like that. Once you start diving into the 480 volts, you want to really kind of make sure you know what you're doing. And there's OSHA says, well, if you're starting to expose yourself like that, we need protection, PPE. Now you're going to see a lot of electrical people working on controls that aren't wearing a lot of PPE, me included. So I get to be a little bit like a cowboy sometimes and think that but if there's something that happens, if there's a short circuit that happens and you're working on a motor starter that's got a 100 amp motor on it, you're going, wow, if I short that out, there's going to be a lot of sparks. This is a true story. I worked for Northern Improvement at the time, I was more electronically trained than I was electrically trained. And that's one of those things but I was electrically trained, but not so much there was safety and probably common sense. And one of the common sense things is I put a short across a 480 volts. They wanted some lights to go out in the field, and they says, well, we check these out before they go out. Well, I was a bit of in a hurry. And so I just took those leads and I put them up against the 480 in a circuit breaker, and it was shorted out to check to see if it was going to work. Well, it was shorted out. And talk about arc flash. I was watching. I thought I was walking through the pearly gates. The light on that was so bright. I turned to the side, and that brightness was still there. Person that was working with me said, "Clarence, there's a flame 6 feet behind you." It ripped off the skin on my fingers. It burnt the hair. It singed me. I looked straight into it. The blast from it peppered my eyeballs. They drove me to the hospital in my own truck, and they put some salve in my eyes, sent me home. For a day, my eyes were closed. It gave me a lot of time to think about what the hell I just got done doing. And I didn't want to do that again. And I didn't do that again. Then I don't want you guys to do it again. What would have been the proper operation for that? Go to the circuit breaker panel, flip that off, take these wires and stick them to the circuit breaker, go back to the panel, flip it on, and the circuit breaker would have turned off quite quickly. It wouldn't have been very happy with that big short I put across it, but that would have flipped back again. So I'm just saying that I'm telling you, I don't want you guys to be involved with it. I don't want to scare you out of wits. I want you to scare you into your wits, because I have since then been doing a lot of 480 all the time, but I have my wits about me. So this is what we're going to get into. OSHA says if there's a arc flash, they want you prepared for it. Sometimes the equipment that they're asking you to be protecting yourself against in some of those instances is very, very difficult to be working with. So I'm going to give you some ideas about that, and then we can discuss it going forward on how to be more safe.
That symbol can only be used if the product successfully completed testing to the agency's standard, which is based on national or international standards. UL 3111, for example, is based on IEC 1010. In an imperfect world, that is the closest you can come to ensuring that the multimeter you choose was actually we changed this module to safe meter usage instead of meter usage because this is where the rubber meets the road. This is where you take your knowledge and put it into practice. If a mistake were made, this is where consequences get to be the greatest. Before we get excited about fixing things while in harm's way, let's get excited about protecting ourselves while in harm's way. Seatbelts, airbags, and defensive driving do not prevent all fatalities. They take a big bite of taking risks, and now the odds are more in our favor. Shock, electrocution, arc flash, and arc blast are responsible for one fatality every workday in the US, and some 8,000 workers are treated in emergency rooms for electrical contact injuries each year. Enjoy the electrical challenge. Put your seatbelt on. Drive defensively. Hope your airbag works.
What voltage source should be verified to be disconnected before working on a motor starter? Choose all that apply.
Out here, Jason.
All the above?
all the above. You got 120 volts in there and you have got 480 volts. 480 volts is pretty easy to detect where that comes from because it goes to the top of the circuit breaker and out. Normally you've got compartments that these guys here that your motor starters and circuit breakers are in. So if you flip off the circuit breaker, the main circuit breaker, you know for one thing, you're cutting off the 480. You don't know all the time if you're cutting off the 120. And so sometimes your 120 comes from a little transformer. In each box, they have their own transformer. And sometimes the 120 comes from your circuit breaker panel, where all of those starters, coils are tied to the circuit breaker panel. They're powered up from that. That is the, you're gonna have to go back to that circuit breaker panel on your wall, your 120 volt, and find out where your control circuit there is. Check in here on 1 and 2, terminals 1 and 2 with your meter. Check to see it's got 120 volts to it and then flip it off and see it go away. If there's a transformer in each one, that means when you flip off the transformer, or the breaker is going to turn off the voltage to the transformer, and consequently, you're not going to have any 120 volts power in there. So you have to kind of determine that at your plant. Does your motor controls have a little transformer in there to supply the 110 volts for that particular circuit? If you got 10 starters, you're going to have 10 independent transformers. That's how that works. If you're doing it off your circuit breaker panel, you got 10 starters, but you only got one circuit breaker, that's going to turn that off at the lighting panel. So thank you very much. Jason.
The correct answer is C, all of the above. The 480 volt AC connected to the starter contacts and the 120 volt AC sourcing the start, stop, push buttons.
Properly helps in the troubleshooting and repair process. The meter is also used to confirm that a circuit is safe to work on when touching components that were once energized with voltage. Sometimes a component like a starter is supplied with voltage from two different sources. This means that tripping the disconnect supplying the 400 volts AC to a starter contactor does not disconnect the 120 volts AC being supplied to the stop-start control terminals on the motor starter
Okay,
circuits.
so look in here, I'm not seeing a transformer in here. I am seeing a, but there could be one under that. There could be a transformer right there. And a lot of times they'll put fuses on that. That means if I flip this off, it not only takes away my 480, it takes away the 110 volts that would take in order to energize what you have here.
Clarence, would you like me to
Therefore,
throw
it
up
is
that
important to
power?
understand circuit power.
Would you like me to throw up that control power drawing for just a moment of the
Let's
three
not do
different
it yet.
types?
Let's, but I'll
Okay.
keep you in mind on that.
Okay.
Before working on it.
When working hands-on with a motor control circuit, what is required to verify that power is not present? Select all
Okay,
that
I'm
apply.
gonna pick on Justin. Okay, A. Well, what we want to do here is we're going to get our hands in there. We're going to be on the load side of that circuit breaker doing some work. We don't want no voltage in there. We don't want no surprises. Okay, so A, check the voltage in a known power source, such as a line set of a motor feeder breaker to verify that the meter works. Is that a good idea?
Yeah,
Okay, we're prepping our meter. We're making sure that when we're going to go to a place where there's no volt, we're expecting no voltage, that the meter is actually working right. Okay, how about B? Check for 0 volts. This is where that probe is at. That's on the load side of that circuit breaker. Check for 0 volts on the load side of that motor feeder breaker from each phase lug to ground. So Now we're gonna be going, I'm on phase B. And if I go over and screw, that's phase C, phase A is on the left. So it's saying check for 0 volts on the load side of the motor feeder breaker from each leg, each phase log to ground. So is that a good thing?
Yeah, I'd do that.
Okay, we want 0 volts.
Yep.
Here's a check for 0 volts on the load side of the motor feeder breaker from all 3 combinations of one phase to another. So now instead of just having that one lead going for there and the other one being on your ground lug, in there, find a ground lug. But this says it wants to go from A to B, A to C, and B to C. Is that a good idea?
I mean, you could, but you really wouldn't have to.
I think you're absolutely right with that. You could, but you really don't have to. And Chris probably feels the same way too. If he doesn't feel the same way, then Jeff, straighten him out.
I don't know if you had a ground issue though, and you wasn't grounded well, you could still see it phase to phase, but not see it to ground.
Okay, well, let's talk about that a bit. If you're going from, yeah,
I would still go phase to phase to verify you got a ground, just to make
okay,
sure.
well, you would have a ground because remember up here, we checked from a known power source.
Oh, okay, gotcha.
Okay,
I do
So-
it anyways, just to cover my own hind end. I always
that's kind of
go
what I do
ground
too.
phase.
That's kind of what I do too, but Justin, I kind of feel how you are, but you know, sometimes going, hey, really, I really want to be sold on this. But I think the main thing to really prove it, make sure your voltmeter works on the line side, and then go from each lug to ground. Okay, so here we're probably going to tell you to do that, but Justin, I agree with you. It's a little bit overkill when it comes. It's a warm and fuzzy feeling. How about you check for 0 volts on the loads of the motor from all 3 combinations of one phase? We just talked about doing that. And so, how about E? Verify there's no voltage in the control circuit.
Yeah,
That important.
yeah. You could.
Verify again that the meter works.
Yeah, that's important.
How about trying to start the motor? Would that be a good thing to do?
No.
What I would say is trying to start the motor. If you remember when we were going into safety, I believe did you take the safety day, Justin?
I did, yep.
Okay. Remember there that we steps for lockout tagout, and one of those was to verify that after you've done your lockout tagout, try to start it up. If it starts up, then going surprise, surprise. So this is one of those things OSHA likes you to do. So I would say try starting the motor, and that's kind of a way to verify. So I don't think that's entirely out of the question. Thank you very much, everybody.
Bye. The correct answers are A, check the voltage on a known powered source, such as the line side of the motor feeder breaker, to verify that the meter works. B, check for 0 volts on the load side of the motor feeder breaker from each phase lug to ground. C, check for 0 volts on the load side of the motor feeder breaker from all 3 combinations of one phase to another. D, check for 0 volts on the load side of the motor starter from all 3 combinations of one phase to another.
Okay, so we went from breaker to the motor starter. I'm not sure the motor starter feeds the motor. That's a little bit overkill, but the circuit breaker is what you wanted to shoot for.
E, verify that there is no voltage in the control circuit. F, verify again that the meter works. And G, try starting the motor.
Lockout tagout procedure could be renamed lockout tagout verify. If this 480 volt circuit were to be worked with hands-on, The breaker disconnect must be tripped, of course, before doing so. The verify step in this instance does not mean the circuit is safe to do hands-on work, just because the breaker disconnect is locked out, and the push of the start button did not pull in the contactor. Does not mean that a faulty breaker disconnect properly disconnected all three phases from the load side of the breaker. A breaker disconnect's contacts sometimes weld to the breaker disconnect's terminals when overworked, shorted to ground or another phase. The breaker disconnect lever or toggle lever may appear to work normally externally, but may not be working right internally. When working on just the mechanical part of equipment, verify may mean just trying to start up the equipment. When working on the electrical part of the equipment, it means verifying there is no voltage present on the load side of the breaker disconnect. It also means wearing arc flash PPE whenever verifying that power is not present. Ask your safety director about the procedures for your application. Add these procedures to your written energy control procedure. When working hands-on with the electrical in this motor control circuit, the verify step means verify the meter works by measuring voltage at a known source, such as the top of a breaker, by measuring from a phase to ground. Verify that no voltage exists from each phase to ground and phase to phase. Verify no control voltage exists in the control circuit. Verify again that the meter works. Electrocution, overhead crane servicing and maintenance. A millwright is assigned to a servicing and maintenance task on an overhead crane. The employee initiates the prescribed energy control procedure by turning off the crane's electrical disconnect switch and placing his lock onto this energy isolating device. However, the disconnect switch lever is corroded, allowing it to physically separate from the disconnect switch assembly. As a result, when the millwright places the lock on the lever in the off position, the stub located inside the electrical box remains in the on position. The employee does not attempt to verify de-energization by using the crane start button. When he contacts the energized electrical bus bar located near the bridge railings, fatal injury results. This repairman was trained in the requirements of a lockout-takeout standard as an authorized employee. He was not, however, trained as a qualified person under the Electrical Safety-Related Work Practices Standard. The repairman was not adequately trained as a qualified person under the Electrical Safety-Related Work Practices Standard to perform lockout and tagout of electrical components. As a result, he could not have adequately verified that the circuit was de-energized. Please read the following on your own.
We'll walk you through.
Few realize how little current and how low a voltage are required for a fatal shock. Current flows as low as 30 milliamps can be fatal. 1 milliamp equals 1/1000th of an amp. Let's look at the effects of current flow through a typical 150-pound male. At about 10 milliamps, muscular paralysis of the arms occurs, so that he cannot release his grip. At about 30 milliamps, respiratory paralysis occurs. His breathing stops and the results are often fatal. At about 75 to 250 milliamps, for exposure exceeding 5 seconds, ventricular fibrillation occurs, causing incoordination of the heart muscles. The heart can no longer function. Higher currents cause fibrillation at less than 5 seconds. The results are often fatal. Now let's calculate the threshold for a hazardous voltage. The approximate body resistance under the skin from hand to hand across the body is 1000 ohms. A voltage of only 30
Okay,
volts
you guys get the idea.
ceases to exist. It is punctured by the high voltage. Electrical currents clamp the heart muscles and prevent ventricular fibrillation. Such currents will cause severe burns and unconsciousness, but the victim will usually respond to artificial respiration. Artificial respiration must always be applied immediately if breathing has stopped, and maybe CPR. Familiarize yourself with the following procedures for the rescue and care of shock victims. 1. Remove the victim from electrical contact at once, but do not endanger yourself. Throw the switch. If you are unable to de-energize the equipment immediately, use a dry stick, rope, belt, coat, blanket, or any other non-conductor of electricity to drag or push the victim to safety. Determine whether the victim is breathing. Keep him lying down in a comfortable position and loosen the clothing about his neck, chest, and abdomen so that he can breathe freely. Protect him from exposure to cold and watch him carefully. If the victim is breathing, treat him for traumatic shock. Keep him quiet and warm, but not hot. Cover him with a coat or blanket to conserve body heat, and elevate his feet slightly, 12 to 18 inches. Treat any visible burns and stop any visible hemorrhaging. Some traumatic shock, often called shock of injury, is always present in injury cases, and sometimes does not develop immediately. It frequently causes death even though the injury itself was not fatal. Keep the victim quiet and prevent him from moving about. After electric shock, the heart is very weak, and any sudden muscular effort or activity may result in heart failure. After a severe electric shock, patients sometimes die from the effects of shock or injury after they have been revived. Send for a doctor at once, and do not leave the victim until he has adequate medical care. If the victim is not breathing, it is essential to apply artificial respiration without delay, even though he may appear to be lifeless. It illustrates how loads become energized, whether they were meant to be energized or not. High pressure seeks low pressure, and will push electrons through filaments as well as a once beating heart. Enclosures are grounded, and the return side of the circuit is wired directly to the enclosure. Touching the enclosure with one hand and at the same time touching terminal 1 or 2 with another limb can electrocute a person. When Homer is touching the high pressure side of the circuit, but not the return side of the circuit, he has not completed the circuit. Therefore, the current is not flowing through his heart, and he is still alive. If he completes the circuit by just merely touching the enclosure door, the high pressure on his right hand will seek the low pressure on his left hand, and Homer could be a dead man. Standing in shoes with wet boots on wet ground while touching the power supply terminals could also kill you. Wear PPE when possible. Ground one lead of the voltmeter with a clip lead and probe with one hand. If only one limb comes in contact with voltage, the chances of injury are minimized to slim or none. Then you are performing a series of measurements on an electrical service panel. You have just finished measuring a small current draw for some ancillary piece of equipment, and you want to measure the circuit voltage so you can calculate power consumption. Your assistant is holding the meter and switches it from the current function to the voltage function, but forgets to switch the test leads from the current terminal to the voltage terminal. Pow! Another common meter misuse can occur when making a resistance measurement. This happens when you make contact with a circuit you thought was dead, when it was actually live. Modern multimeters generally have good overload protection and recover automatically. Their designers usually get this overload protection by inserting a thermistor in the ohms circuit. This component increases its resistance rapidly with the heat from overload current.
When checking voltage, current, and resistance on a faulty circuit with a digital meter, the meter design and test leads will protect the operator in case of incorrect meter usage. True or false?
Help me out, Jordan.
They're designed to, but it doesn't mean that's always going to happen if you're not sure of what you're doing.
The correct answer is
Could you
B.
hear me?
Yeah, I did. And very good. So is that true or false?
Well, I'm guessing it's false. Now, I thought they were designed to, but if to a point, I suppose.
When checking voltage, current, and resistance on a faulty circuit with a digital meter, the meter design and test leads will protect the operator in case of incorrect meter usage. True or false? For the most part, that's true. but there's always those cases that you I would be entirely dependent on that. Is that thank you.
They're saying if you
E,
use it wrong, that
false.
you're,
Good meter.
you're leading the wrong spot. You're not protected.
True. Thank you, David.
Okay, thanks.
Design and proper test leads are no substitute for incorrect meter usage.
Leads, which are still connected to the current terminals on the meter to the voltage buses, a direct short across
So
the source
you
volt.
have this thing in ohms, or if you have this in amps, and you're going across right there, if it catches you by surprise. Typically, your safest thing to be doing is using your meter for the voltmeter and punching around. When you go into the ohm meter, you got to put it on your thinking cap.
Voltage occurs inside the handheld multimeter through a low value.
Talking about fuses here and getting the right fuses in there. Now we're talking about some PPE. Some of this PPE you're going, wow, okay, possibly
Burn
work
injuries
in all
when in the
this.
proximity of an energized.
It's so heavy and so here we got these big gloves and some rubber gloves. This is 480 in there. We've got a circuit in there, a circuit breaker that trips at and it's fused for like it trips at 30 amps and this is like for 480 volts. That's going to have a smaller arc than you're going to have if you have a breaker that's 100 amps and 480 volts. So it kind of because the heavy stuff gets so bulky, I try to make it a thing where I am doing my troubleshooting in what's called an 8 calorie. It's if I do get exposed to any arc flash, it's going to do some protection. It will be enough protection in most of the things that I get into. And if the blast is a little bit bigger than that, it's going to at least protect me from that blast considerably. A lot of things you want to do is protect your eyes are very, very important.
Higher voltage circuit. Severe burns can happen when exposing oneself to an open enclosure with higher voltage present. The enclosure must be labeled with warning labels about the arc flash hazard. The operator is using a temperature gun aimed at the terminals to look for excess heat generated when terminals and wires are not making good connection. The rubber glove inside a goatskin glove not only protects against arc flash, but insulates the troubleshooter from coming in contact with the circuit.
I normally
Installation of the
don't do my probing around with gloves on. I just do it with my hands. I got my fingers at the cable end of the probe, not if they're close. I typically am going to be probing around with one hand. And then just for arc flash protection there, like around my face, a face visor gets to be important. Wearing cotton, not synthetic, is a good thing to be working with. Cotton's very important. Some of your 8 calorie suits are made out of Nomex. Nomex can take the heat better than cotton.
equipment. OSHA may sometimes require the verification check as measuring the voltage at the main disconnect, and OSHA may sometimes require the verification check as only engaging the start button to confirm the machine is inoperable and then return the switch to the off position before proceeding with servicing.
Lockout takeout could be you could say that once you do your lockout tagging out, you can verify or lockout tag out, test it, test to see if the thing is going to start up.
I want to ask a question, and I really don't know for sure.
Okay, let's hear you.
Can you hear me?
Yes, we can.
Anything I've done at a plant, I've never had to use anything but ohms or voltage, but why would you ever be checking ohms with any power on at the plant if you're just checking resistance?
Um,
Voltage, I could see where you're checking with power on, but why would you ever check ohms with power on?
you would not. It gives you a bad reading and it hurts the meter and it might hurt you. Typically, it doesn't hurt you. It's gonna be blowing a little fuse inside. I'm just kind of bringing up some worst case
Yeah.
scenarios here, but no, you would never do that, Jordan, not with power on. And I'm not suggesting we do. It's
Yeah,
just
so
maybe. Go ahead.
no, so yeah, so most of the time, like where I'm coming from, you're only gonna ever have the meter set in two places, and you're gonna be either checking ohms with all the power off, or you're checking voltage, and you obviously you'll have to have power to be checking voltage.
Or sometimes you're looking for the
Right.
lack of voltage. True, true, absolutely true.
Yeah. Okay, thank you.
You bet. Anybody needs clarification on stuff, let us know.
Necessary for your application. This step is most important and often overlooked. It may not be necessary or prudent to check if the voltage has been disconnected at the electrical breaker when verifying if the equipment is now rendered inoperable by checking with a test meter. In some cases where the mechanical equipment is being serviced and the electrical circuit is not being worked on, verification of the equipment inoperability may be accomplished by trying to start the equipment after it has been electrically locked out. OSHA requires arc flash personal protective equipment, or PPE, to be worn in cases where personnel are exposed to high energy short circuits and electrocution. Therefore, minimizing exposure to the inside of high voltage cabinets is prudent. Injured two ways: electrocution and severe burns. High voltage short circuit happens. Explosions like this can happen. Being in the vicinity without the PPE can cause serious injury. New in 2009, Arc Flash Protection and NFPA 70E. What is the NFPA 70E? Both the Occupational Safety and Health Administration, OSHA, and the National Fire Protection Association, NFPA, have written standards and regulations that build on one another and help keep all workers safer from electrical hazards in the workplace. In this case, the OSHA regulations and NFPA standards work so well together. It's been said that the OSHA provides the shall, while NFPA provides the how.
And so the how gets to be where we're going to, for each particular piece of equipment enclosure, we're going to start to say what kind of PPE we should be using. And some of the PPE that you're going to see out there is 8-calorie suits and some is 40-calorie suits. 8-calorie suits is something that you can find yourself working with and feeling comfortable with it. When we get to 40-calorie, it looks like you want to disarm a bomb and get that kind of protection. This shows the closer we get to something that the higher the PPE should be.
Safety has a price. Consider the price of being injured. Many typical items which enable the electrical maintenance.
Okay, so what we're seeing here is this is an 8-calorie soup. These gloves are a little bit bigger and clumsier. This isn't anything I would really typically be working with. The protecting my face is good. This is an 8-calorie mask with it's protecting my face and around my ears and up around there. This is a Nomex jacket. Heavy cotton can help out there. I'm not quite sure why I need to have something that thick, but this is one of those things doing what I could to work with a different kind of protection to see how I would feel about that. So if I'm working on something that's got small breakers on and stuff like that, I'm gonna feel pretty good with that. But here I'm finding out that now we're into some bigger breaker stuff, and look at, that isn't anything that anyone is particularly gonna feel comfortable to be doing any troubleshooting with. So, and you're gonna find out that more cases than not, people just aren't gonna wear them. Well, I would say, you're better off with this than not wearing anything at all. So that's basically what I do. Most electricians you aren't gonna see end up using this very often. Um, they feel it's more cumbersome. Although it is a requirement by OSHA, it's anything that, a lot of electricians are saying, this is just too cumbersome, I can't get the job done. So, the things that could be in this bag is like safety glasses, steel toe boots, what they want, rubber gloves, leather gloves, hard hat with a face shield, 8 calorie. It says a synthetic smock. You don't want a synthetic smock. It's got to be a Nomex cotton one. All these things should apply except for that guy there. A 40-calorie full body suit with a hood. Um, you can see that as a requirement, but that just really isn't used. So I would say an 8 calorie Nomex one is the kind of one that you want. And it's really, it isn't cumbersome at all. So I would say whenever you get in front of an electrical panel, putting on some kind of a face shield gets to be important. Put on something like a heavy cotton shirt or a leather welding jacket, something. Give yourself a little protection. Get something there for your face. Get some gloves on if that makes you feel more comfortable at what you're doing. This could be compared to motorcycle. Motorcycle, you don't know how the other guy's gonna do. He could surprise you at any time. Back in my teenage years, I did have a bike, and I'm finding twice people didn't see me, and I'm going, this is an accident waiting to happen, so I kind of gave up on bikes. Now this is something that can be kind of interesting in this meter right here. It's made by Fluke. It says, okay, let's de-energize it. Let's put this our meter in there, and I'll get a clip it because I want to be taking some readings here. I want to close the door, then I want to turn on the power, then I want to read what's going on inside there. So this is like a removable head. That's kind of interesting. Here we're showing that this guy is doing some testing inside of wherever he's at. And here I've got my meter inside, and I kind of close that up. These are just some kind of tools I'm kind of giving you some ideas on. Here we're showing a control panel that's got 480 volts to it. And then we also got some 110 volts. There's a transformer, you got 480 volts on there, and you got 110 volts there. Here are some circuit breakers that got 480 volts. Here's your main power coming in. On the outside, I got some instrumentation on these VFDs where I can actually read things on what's happening on my VFDs outside of it instead of having to do it on the inside and do the programming. So you can actually pop these things right off the VFDs and put them on the outside. Start-stop buttons are there as well. These here circuit breakers got safety guards over where you really can't get your fingers in there. And so that's always a good design. Here we got transformers, you got terminals here, but it's got safety guards over those. So you're not gonna really bump into those. This here terminal strip should have a little plastic guard over it. I'm not sure if it's there or not. So they've made it very hard for you to get your fingers in there. All our 480 volts is the bottom side, and it's all kind of guarded. So basically, this is pretty safe from you from going around touching things. A lot of times I have to make sure if I'm there's some 480 volts in there, and there's some open terminals, that I'm always leaning back, so I'm not going to be falling in. No one's going to come by and bump me, or a door slamming closed because of the wind. If I were to do this one here all over again, all the 110 would have been in one box, and all the 480 volts would have been another box. So if I want to do some work on the control part of it, these would have been separate. These are some things that if you want to make sure the 480 volts is cut out, these are the different lights that you can hook up to the 480 volt power. You hit your circuit breaker there, you can see that go away. Okay, things are safe. Now, this here isn't smart. Instead of going into the control house and saying, go ahead, hit my drag, this guy's pushing this circuit breaker, or not the circuit breaker. This is the armature on a starter. When he pushes that up, his drag's going to start. If there's a short on your drag, you're in trouble. Now, a lot of times where it's the most dangerous when it comes to starting up equipment is when you do it for the first time, or you get when you're first wiring up things. You don't, first of all, you don't know if you're wiring up a shorted load or not. You don't know if it's really wired up correctly. So when starting up, and I was working with the electricians at the time, and they're and you would be hearing communicate with them, each other. This is a first start. This is the first time we're going to be starting up this conveyor. It's the first time we're going to start up this bucket. It's the first time we're going to start up this the dryer. That first start means get away from all the electrical equipment, and then when you start it up, then it will go and do its thing. But if there's something that's not going to be right, it's going to explode without people being around. So typically that's where your problems are. Or if you're doing some working in there and you have a screwdriver and you drop a screwdriver across something by accident, that can cause this kind of thing going on. But the purpose of that motor starter is it's an electromagnet to do this remotely, to close that switch from a remote point. Here he is doing it right up front. And if something goes wrong, he too is going to look like me about 50 years ago.
Voltage with a high current short, and you can get a big bang.
What are the main reasons for using a motor starter?
Help me out, Jordan.
A is true. A and B, I would think.
Yep. D is a really interesting one. I'm not sure if it comes up with these answers. That's kind of crazy. Thank you. A and B.
The correct answers are A, remove the operator from the inrush of current, and B, protect the motor during overload conditions.
Several reasons. One reason is to remove the operator far from the inrush of current. If a 480-volt power problem develops in the circuit, the wiring to the motor, the starter breaker is designed to take the heat within reason. The starter overload trips when the motor works too hard, or the breaker trips when the motor or wiring shorts to ground or shorts phase to phase. Sometimes when a short happens, the breaker's interrupting capacity is not high enough, and the breaker or starter blows up like a bomb. The following quote is from a person who experienced such an event. I, Clarence Richard, experienced a situation much like this once so far in my lifetime. At the time it happened, I thought I was passing through the pearly gates. The sun was blazing into my eyes, no matter which direction I looked, whether my eyelids were open or closed. My hair was burned and the skin was peeled back on my fingers. I had a day of near blindness to think about if I should be tweaking my procedure. My excuse was that I was not trained. What will your excuse be?
Which of these are important for working safely with electrical circuits?
Okay, help me out there, Nick's iPhone. Is A important?
Yep.
B,
Yep.
C,
Yep.
D,
No.
E,
Yep.
F,
Yep.
G.
Absolutely not.
H.
Yep.
Okay, nice job. See what this guy's wearing? You know, that's good to wear. That's a good line of defense. Get somebody there to cover your eyes. Got glasses and put a face shield on if you can. Get some gloves that are that work for you. Wear jeans, wear cotton shirts, button it up.
The correct answers are A, be alert, B, know how the circuit should function, C, work on de-energized circuits if possible, E, use proper protective gear, F, use proper functioning and verified test equipment, and H, verify a de-energized circuit using the three-point test method. Check the voltage at a known source, check the voltage at the circuit in question, and check the voltage at a known source again.
Safety is everyone's responsibility, but ultimately, it's in your hands. No tool by itself can guarantee your safety. It's the combination of the right tools and safe work practices that give you maximum protection. This person is wearing a Nomex shirt, a face and ear shield, and using a voltmeter with a Cat 3 safety rating. Here are a few tips to help you in your work. Work on de-energized circuits whenever possible. Use proper lockout-takeout procedures. If these procedures are not in place or not enforced, assume that the circuit is live. On live circuits, use protective gear. Use insulated tools. Wear safety glasses or a face shield. Wear insulated gloves. Remove watches or other jewelry. Stand on an insulated mat. Wear flame-resistant clothing, not ordinary work clothes. When making measurements on live circuits, hook on the ground clip first, then make contact with the hot lead. Remove the hot lead first, the ground lead last. Hang or rest the meter if possible. Try to avoid holding it in your hands to minimize personal exposure to the effects of transients. Use the 3-point test method, especially when checking to see if a circuit is dead. First, test a known live circuit. Second, test the target circuit. Third, test the live circuit again. This verifies that your meter worked properly before and after the measurement. Use the old electrician's trick of keeping one hand in your pocket. This lessens the chance of a closed circuit across your chest and through your heart. Let's take a look at a worst-case scenario in which a technician is performing measurements on a live 3-phase motor control circuit using a meter without the necessary safety precautions.
And through that. Here we're
Generally speaking, Cat 3 is used for 600 volt and 400.
okay. This here tells you you've got a Cat 1, 2, 3. This one here has a Cat 2. So this one here does a little bit, it does better protection than the other one, but Cat 2 gets the job done. I've seen some meters that are very scary if when you are to be working around 480 volts with. So use an industrial grade one. Fluke is always a good choice. These magnets on here strapped like that are very, very handy. What we got here?
Safety problem when someone is checking a circuit for no voltage before they physically touch it. Meters are sometimes called multimeters because they can multitask. They can be used to measure voltage or current or resistance, etc. The meter on the right is an auto ranging meter with a simple function selector switch. It has a busy looking display that displays the value as well as the function in engineering units. On the left is a manual ranging meter and has a busier function range switch that adjusts for range as well as selecting the function. The auto ranging meter requires special attention paid to the units of measurement.
I'm saying up here, just because you have a number here and you have it on voltage, and if it says 120, doesn't mean 120 volts. It might be 120 millivolts. So you're going to have to look up here when this does its thing, what you're exactly doing there. That's this other one here. If you put it on both, that's what you're kind of expecting it, and then you see those numbers that you end up figuring that out a little bit better.
And discharge all capacitors. Normally, capacitors are not an issue if you are not troubleshooting problems on circuit boards where capacitors are normally found. If the magnitude of a signal to be measured is not known, set selector switch to highest range first and reduce until satisfactory reading is obtained. Strictly observe the max input limits when measuring voltage or current. Important. Notice that the probe is being held at the end of the probe. In this slide, we are just measuring resistance with power off. The technician is careful not to be part of the circuit by directing the probe tip from as far away as possible. Many times, beginner troubleshooters slide their fingers down as far as the finger guards. This is unnecessary and should be avoided. The troubleshooter should clip one lead to ground and probe with one hand. Normally found in electronic circuits. If you have more interest in capacitors, you may read the following notes yourself.
We don't. Any interest.
With the corresponding units of measurement being displayed to the right of the numerical value.
So look at, if you're in volts, this is the unit of voltage. If it okay, so so if it says V over here, that means you're reading volts. If it says MV, where are you at, MV? For some reason, we're not seeing MV on here. It's probably because I got it covered up for some strange reason.
It's there just above volts DC on your zoomed in picture. There's millivolts DC above it. I'm not sure what you're looking at there, but on that range switch, you got your volts AC, volts DC, then there's a millivolts above that on your range switch there. There you go. Just to the left of that is your millivolts.
Okay. But that's okay.
So those actually don't do what you just said. That's how mine is too. You have to set it for millivolts. It won't read millivolts on volts.
Okay.
But mine will switch between AC and DC. My millivolts is just defaults on AC. So then you have to push a button to make it switch to DC millivolts. But if it goes to sleep while you're taking a measurement and then you wake it back up, it reverts back to AC millivolts. So now you're getting a bad reading if you didn't notice that happened. So I've had that like kind of mess me up where I had a certain amount of millivolts I was expecting and my thing went to sleep and I woke it back up and now it's giving me a different reading because it switched to AC when I had it on DC.
There's 1,000 volts. I mean, there's 1,000 millivolts to a volt. There's 1,000,000 microvolts to a volt. So you can get some very tiny stuff. When you're reporting to some of the people helping you troubleshoot, they might want to have something in millivolts DC typically, and that's where you normally get millivolts DC coming from the load cells. So you got to make sure you have it on DC, and then you're and be looking for the millivolt range. This is for ohms. This is for mega ohms. That's mean millions of ohms. Kilo ohms, hertz, kilohertz, megahertz.
FYI, there is 1,000 ohms to a k ohm, 1,000,000 ohms to a meg ohm, 1,000 millivolts to a volt, and 1,000,000 microamps to an amp. The manual ranging meter forces the operator to adjust the selector to the proper range, making the operator aware of the units of the value being displayed. The operator must make a conscious effort to interpret the engineering units when reading the value. Danger: do not measure voltage when meter is set to measure resistance. Turn off power to the resistance to be measured and discharge any capacitors. Any voltage present during a resistance measurement will cause inaccurate readings. Connect red test lead to volt-ohm input and black test lead to COM input. Set function and range switch to the desired ohm position. Connect test leads to resistance or circuit to be.
We've been going at this pretty steady. It's 235 right now. Let's come back at 240. David, could you put up a poll? And these guys can get it done in between then. And we'll check real quickly if you're going to need a slide that goes with it.
This one just says 3 from circuit analysis. This is referring to the circuits. So we probably have to have a.
Do I need the electrical one on? Is that what I need?
Yeah.
Okay, I'm at 5252 of safe meter usage. Therefore, I'm going to have to get back to I'm going to circuit analysis too.
Yeah.
What am I doing here?
Wire and a cable or wire bundle by not having to look at the meters.
one more.
The information provided with parallel circuit of M9 and light. This series
Is this what I need? I think so.
Pretty much, but you need to get the meters up though, because it's, well, actually, no, it's not even saying specific meters. That probably works.
Okay,
It's the same circuit, it just doesn't have the meters on it.
okay.
Now this, yeah, these are referring to certain problems. Like it's, oh, maybe not.
Hey, Clarence or David, are you guys there?
Yep.
Hey, I have to get out of here at 4:30 today. You
Okay.
want me to just put it in the chat to let you guys know if I miss anything important after that, if I could get it sent to me?
Yeah, we can do that. I'm not sure what time we're gonna get done, but probably 4:30 or 5, I would think. So hopefully we can finish up before you have to go.
Perfect. Thanks, David.
Yep, no problem.
You there, Dave? You're around, Dave, Clarence?
Yeah, I'm here. And did you have a question?
Yeah, I gotta go at 3:30 to pick up my kids, and I'll be back after that. I can come back on.
Okay. We can send you a video for the part you missed.
Okay, sounds great.
Okay, it looks like it's probably be good time to go over the polling. So operator turns on switch 1 and 2. Solenoid energizer. Starter does not energize, light does not come on.
Series circuit is
Now
in
I really see
parallel with solenoid. This parallel circuit is in series with switch 1. Series circuits have one load and one load only. In a series circuit, when one part of the circuit fails, the
Switch 1 and 2 are on. Solenoid energizes. Starter and light does not come out. Check out switch 1 and switch 1. That's not a good idea because a solenoid coil comes in. Few people picked out, but no, that's not good. Check 120 volts for terminal for 120 volts. Nobody picked that. That's good. Check for 0 volts at terminal 6. That would keep both of them from coming on if we didn't have voltage here, or if we didn't have 0 volts there. So C would be 1. Check for 120 volts at terminal number 3. That's in common with both of those, and 6 is in common with both of those. So I would probably say, and so most people got those right. So both of those answers would have been right. And then for our second question, the starter does not energize. This guy right here does not energize. Everything else works just fine. So we check at the starter terminal. Yep, that'd be good. Like about 92% of you guys did that. Check for 0 on the other side, and 92% of you guys did that as well. Some people said check at terminal 6. 120 volts or for 0 volts. And that wouldn't be right because we have a flow through right here. Terminal 6, we're going to have 0 volts there because we have 0 volts at our light, and that's got to come for the complete circuit there. So for the most part, you guys got it right. You went right for the terminals on the starter coil itself. Nice job. Then solenoid energizes, circuit breaker trips. So most of you said disconnect the starter coil and home out the coil. That's good. Disconnect the starter coil wire and close switch 2. That would do it as well. So many of you guys had taken both of those scenarios work for you. So we did good. We did good. Thank you very much. So moving right along now, I'm going to move back to number 3, safety.
circuit components, switches, any voltage present during a resistance measurement will cause inaccurate readings. Connect red test lead to when meter is set to measure resistance. Turn off power to the resistance to be measured and discharge any capacitors. Any voltage present during a resistance measurement will cause inaccurate readings. Connect red test lead to volt-ohm input and black test lead to COM input. Set function and range switch to the desired ohm position. Connect test leads to resistance or circuit to be measured. Read resistance value on digital display. Open circuits will be displayed as an overload condition. Measurement of resistance. Measurement of resistance is made in parallel with the circuit, with the power off and the circuit being tested. Resistance measurements should be taken in a range higher than that expected to occur, then reduce the range until a reading cannot be obtained, then move it up one range. The component being tested should be isolated from the rest of the circuit for an accurate reading. If the ohm meter is connected to a circuit where power is on, the meter can be damaged, besides giving the wrong reading. An ohm meter has its own internal battery, and the power must be off in the circuit being tested. The ohm meter is helpful in checking the continuity of any wire conductor. Also, any coil for a transformer, solenoid, or motor will have infinite resistance if the winding is open. In this particular case, the range is set too low, indicating the operator must move it up until he gets a reading. Caution: to avoid possible damage to the meter or to the equipment under test, disconnect circuit power and discharge all high voltage capacitors before measuring resistance. The meter measures resistance by sending a small current through the circuit. Because this current flows through all possible paths between the probes, the resistance reading represents the total resistance of all paths between the probes.
Sometimes isolating something is you have to really unsolder it and then take it. You guys had one of those fuses that was, I don't know, you don't solder those in there. Those things, those little fuses on those I/O boards just pop in and out.
To measure resistance, set up the meter as shown in this slide. Provided here is beneficial to personnel that perform industrial electrical equipment maintenance duties. FYI, the complex meter usage techniques are deferred to the advanced and expert troubleshooting modules. This module teaches and instructs the layman some of the principles and procedures to safely read and understand, in this virtual reality classroom, what they must do and be aware of in the real world. Electrical is fun and challenging for those prepared for and excited about the opportunity to manipulate it. If you do not meet these requirements, we recommend you use this information for academic purposes only, and not for actual practice. Some disasters happen in and out of our control. Our first line of defense is being keenly aware, skilled, and knowledgeable. Our second line of defense is working with proper PPE, test instrumentation, and safety equipment. Our third line of defense is working with people knowledgeable in first aid. You will learn that even at times when you are following proper procedures, equipment and test instrumentation fails and accidents happen. A fierce fire explosion can wipe you out unless you are prepared. This module teaches you about PPE, personal protective equipment, and using various meters in various applications, and discusses meter safety and safe meters fit for the 600-volt application. This course addresses the duties required by electrical maintenance people for maintaining equipment powered 600 volts or less, US 480 volt, electrical distribution systems. The PPE, personal protective equipment, being worn by this industrial electrical equipment maintenance person has been recently required by OSHA to address arc flash concerns. Although not required, to our best information, the test meter used should meet safety ratings of Cat 3 600 volt. A meter with this rating, Cat 3 600 volt, UL or CSA listed, or above, Cat 3 1000 volt, UL or CSA listed, is recommended. By wearing appropriate PPE as shown, a lower Cat rating may appropriately protect the meter operator. Energizes, actuating the dryer starter, which supplies 400 volts AC to the dryer motor, and closing the holding circuit.
Okay, we're gonna go into some troubleshooting now. Now that I scared the wits out of you and back into you,
Troubleshooting
let's do
technique
some
steps.
troubleshooting.
1. Take time to focus on the problem at hand. 2. Relax and think clearly and thoroughly through the problem to the solution. 3. Remember to ask and look for help when unsure, especially if added downtime and catastrophes may be a result of experimentation. When you get to where you don't know what you are doing, call people who do. If you can't get them right away, call others or wait. 4. Don't fret. You don't need this job anyhow if management is asking you to be foolish. Many times, management does not understand the gravity of the situation. Management does not really want to take chances on serious damage, and you must remind them of that. With this in perspective, we go through Plan A while keeping Plan B on the back burner. Plan A. What are all the symptoms? When did it start causing the trouble? Was it all of a sudden, or did it steadily get worse? Is it consistent or intermittent? How can I analyze it, and with what? What suspected component spares or system identical components can I use to swap or compare test measurements? Who is my best mentor to call, and when is the best time to get him? Plan B. How can I make the process safely work until a solution to the problem arrives? Motors are used all over the plant to move material and gases in augers, pumps, fans, blowers, conveyors, etc. The electricity is turned into a mechanical force, as current in the motor's coils creates electromagnets, causing the motor to turn. Motors around industrial plants are normally powered by 480-volt, three-phase power. Every horsepower of a motor requires about 1.2 amps of current flow when the motor is required to work at full horsepower capacity. A 100 horsepower motor on a conveyor may draw about 120 amps when working fully loaded, and near half that much when loaded at half capacity. If the motor is wired for 240 volts, the motor requires twice the amount of current as a motor wired for 480 volts. Since motors are being used so much, and motor controls being simple and important, the beginner troubleshooting module focuses on this important subject. Load equals too much amperage equals motor working too hard equals short motor life expectancy. The motor works, the more the current amperage flows through the motor. The more the current flow through the motor, the hotter it gets. If the motor gets too hot, it will burn up and the windings will short together, causing the amperage through the circuit breaker to trip. A protection circuit is often used to keep the burned motor disaster from happening by accurately measuring the current flow and disengaging the contactor when the FLA, full load amps, as stamped on the motor nameplate. This protection circuit is called an overload relay. Sometimes motors are more apt to trip overloads when starting up. Large motors build a lot of heat inside of themselves, especially when starting up.
Let's see what this motor here has to say. It tells you some information. One is it gives you a frame size. So if you're going to be replacing a motor, you don't want to do it with the same frame size. So that's some information they're going to want to know. Then there you notice that this is a 2 horsepower and 3-phase, 60 hertz, RPM 1725. Volts, we have choices of volts. We got 460 volts or 230 volts. On the right side, it shows you how you can wire up to the low voltage, or you can do, which is the 230 volts, the 208. High voltage is going to be the 460. High voltage, typically, you're going to take the 3 leads coming from your starter, and you're going to have them going, 1 lead going to wire number 1 in the motor head there, and then another lead going to number 2, and number 3 you're going to, normally what I do is wiring them up, make sure they get good taped up, and sometimes do that with high voltage tape. And then from that point, I got a tie 6 and 9 together, and 5 and 8 together, and 4 and 7 together. Make sure that those are tightly connected and tape them up appropriately. And now that's all set to go for 480 volts. Notice that our amps here says 5.9 to 5.6 to 2.8. The higher voltage you have going to this, the less amperage it's going to use. So, this here tells me at its 2 horsepower rating, it's going to take about 2.4 amps. Typically 1 horsepower is about 1.4 amps. And then if you got 50 horsepower, you take that 1.4 times 50, and then that will give you what that amperage there is, which might be about 70 amps. So that gives you a feeling there for what there is on the motor itself. If you're at 2 amps, that the heater sizes, you're going to be having to adjust that to 2 amps. If your heater kicks out above 2.8 amps, that means you might end up burning it. If the heater kicks out below 2 amps, then you're going to have nuisance tripping. So having that size correctly gets important. That's FLA. You hear us talk about FLA, full load amps, meaning you got full load on the motor. Is going to give the amperage of, and that is going to be 2.8.
The heat generation from starting a motor several times in a short duration can cause the motor to burn up.
Starting and stopping motors gets to be a pain in the butt, especially with big fan motors, 100 horsepower, 200 horsepower. You don't want to be starting and stopping those. There's a lot of internal heat that's happening there, and you can ruin a big motor that way.
Circuit is called an overload relay. This is a side view of one of the 3 contacts on this overload relay. Relays normally have an electromagnetic coil to pull in the contacts. Calling this a relay is a bit of a misnomer, since a coil is not used to open and close the contacts. The contacts open when the temperature gets too hot. It would be better called a thermal switch with manual or automatic reset capabilities. When the temperature exceeds the temperature set point, the contacts open and usually stay open until the contacts are reset. This drawing indicates 2 different portions of 2 entirely different circuits. The top circuit is a conductor delivering one of the 240 or 480 voltage phases to the motor. This conductor feeds large wires to the device, heater, that acts like a conductor or wire, except that has little resistance added to the wire or heater. When resistance is added, heat is generated. The more current flow through the heater, the more heat is generated and dissipated to the thermal sensor, which trips the temperature switch when the temperature switch set point is exceeded. The sensor in this particular design is actually the solder in the barrel that supports the axle of the ratchet wheel. The bottom circuit has smaller wires passing through the switch contacts and to the coil. The coil does not require much current to energize, therefore the wire is smaller. Care must be taken when working on this circuit. Disconnecting the 480 motor voltage many times does not disconnect the coil voltage. When the current flow is below the set point, the ratchet is fixed and does not rotate. Once the set point is exceeded, the ratchet is no longer fixed, and the spring-loaded pawl rotates the ratchet, allowing the contacts to open, and consequently, the coil holding in the contactor is de-energized. The contactor is not supplying voltage to the OL relay anymore, and consequently, the motor stops running and is allowed to cool down before burning up. Heaters come in several designs and shapes, usually dependent on the manufacturer. No matter the design of overload heater, the motor current heater actually passes through a wire conductor. When the motor works too hard and draws too much current, more heat is generated. When the heat of this thermostat exceeds the trip rating of the temperature rating of the trip point, the overload relay trips, causing the starter coil to de-energize and saving the motor from burning up. The heater on the left is a flat resistive wire that radiates heat to a sensor on the bottom side. The heaters in the center and right coil the motor current wire around the thermal sensor. The conductor wire in the center is much smaller than the conductor wire on the right, indicating that the heater on the right is for a large motor. The OL heater symbol on the bottom right depicts the heat source that trips the thermostat that de-energizes the starter coil. A switch, allowing a choice between manual and automatic reset.